In this section of Chapter 4, we're going to talk about substituted cyclohexane rings. The first type of ring we're going to look at is going to be a mono-substituted cyclohexane, so a one-substituent cyclohexane. Specifically, we are going to look at methyl cyclohexane. So we'll take our cyclohexane ring and we will have the one methyl substituent on it. And what we're going to see under these substituted cyclohexanes is that both chair conformations are no longer going to be equal for us. So I want to start off and I'm going to go ahead and draw our first chair structure for methyl cyclohexane. And we can put the methyl group in one of them in the axial position, where if I do my ring flip then for this structure, to keep the methyl group on the top of the structure, with my ring flip, that methyl group now becomes in the equatorial position. So this would just be the ring flip for a methyl cyclohexane. What we're going to see is that the one with it in the axial position is 1.8 kilocalories per mole more stable than the one with the methyl group in the axial position. So if we look at this, the reason being is because of the axial compared to the equatorial. So remember, if we walk around our ring in those axial positions, they're the vertical ones. So we have the methyl group straight up, the hydrogen on the adjacent carbon would be straight down, and then on the third carbon, we're back to having that hydrogen straight up as well. Because we have those two axial positions straight up on the same plane, there's an interaction here, and we refer to this interaction as being a 1,3 diaxial interaction or strain. And this is what is causing the instability when we have that methyl group in the axial position compared to when it is in the equatorial position. So if we look at it on the structure that I have here, the first structure that I have drawn over there, I've got the methyl group in the axial position. So if you'll notice with that axial position, it's here on the top and we've got hydrogens. We have two of them on either side that are still on the same plane. So you can start to see this interaction on the top of this molecule. When I do the ring flip and I put it in the equatorial position, you'll notice that it is out here by itself. There's nothing around it. There's nothing to interact with it. It has its own space around it. So there's no interaction with that methyl group that we have. So we see that when that group is in the equatorial position, we have a more stable conformation than if it is in the axial position. And we're going to see this with all of our substituted rings, that when we have a mono-substituted ring, regardless of what that substituent is, the chair conformation with it in the equatorial position is going to be more stable than the chair conformation with it in the axial position. So I do want to look at this under the Newman projections as well to give you an idea of what we're looking at when it comes to staggered versus eclipsed. So what I'm going to do is we're going to draw our two chair structures, but I'm going to draw them a little bit different than I had them on the other screen, because I want that methyl group to be on one of the Newman projection carbons. So I want it to be on one of those carbons that are all on the same plane that we're going to be looking down. So remember, we look down those carbon atoms that are in the plane. So we'll look down the two carbon atoms here, and we'll look down the two carbon atoms there as well. So I'm going to put the methyl group in that position so we can see it in relationship to all the other carbons and all the other hydrogens that we have. So for this first one, I'm just going to go ahead and I'm going to put it in the equatorial position. So it is there at that downward angled slant that we have. So when I get ready to look down those two carbons, so remember, I am going to take it and I'm going to look at it under the context of being here on my structure. So I've got my down, I've got my up, I've got my 4 in the plane, and I have that methyl group on the 1 in the plane. So we're going to take it and we are going to look at it in that context. So if I look at my carbon atoms, I've got the 1 carbon atom in the front and I have the carbon atom in the back, and they are here on the side. And then I see the exact same thing on the other side, the carbon atom in the front and the carbon atom in the back. From there, my carbon atoms in the front are connected to that CH2 unit going down. If we flip that so it matches the diagram that we have, I've got it flipping down in the front. The carbon atoms in the back, that's where I have them pointing up. So since everything is going to be staggered for us, let me get this. Since everything is going to be staggered, just making my kit match what I have drawn on the screen for you. So since we've got everything in that staggered conformation, the ones here in the front, so my 2 carbon atoms in the front, the hydrogens are pointing straight up. And then I've got a hydrogen going straight out, and then I also have the methyl group going straight out as well. So it's over here on the side. My carbon atoms in the back, so these are my 2 carbons in the back. I have hydrogens pointing straight down. And then I have hydrogens pointing up and out as well. So you can see in this diagram, everything is nicely staggered. Hopefully you recognize this as being an anti-conformation that I have between the 2 large groups. Here is large group number 1. Here is large group number 2 there in the back. And I see this nice anti-conformation, where if you remember, that anti-conformation was the most stable conformation that we could have. So now I'm going to do the exact same thing. We'll look at it in the exact same orientation for the chair itself, but instead of letting my methyl group be equatorial, I'm going to put my methyl group in the axial position. So I'll leave everything the same, except instead of it being equatorial, I'm now going to put it in the axial position. So when I get ready to draw all of my Newman projection, the carbon over here does not change. What is going to change is that carbon with the methyl group. So they connect down to the bottom. We've got a hydrogen pointing straight up and a hydrogen pointing out. Over here now I have a methyl pointing straight up in the axial position, and I have a hydrogen in that equatorial position. In the back, there's my CH2 unit, hydrogens pointing straight down and going out to the side as well. So you'll notice I've just changed the position from being axial to being equatorial to being axial. So what you'll want to notice here is we're still staggered. So remember, it's still a chair. We are still staggered, but now these 2 large groups are side by side in that staggered. So remember, this is our gauche conformation, and it is not as low of energy as what the anti-conformation is. It is still staggered, it is still a low energy, but it is not nearly as low of an energy as what the anti-conformation is. So this is another reason why when we put groups on our cyclohexane ring, we want to make sure that those groups go in the equatorial position, and that is the more stable or the favored chair. When we look at this, with both of them not being equal, the substituent is always going to be more stable in the equatorial position. The larger the substituent becomes, remember we only looked at a methyl group, the larger this substituent becomes, the stronger those 1,3 diaxial strains or interactions become, the more non-equivalent these 2 chairs become, where we can make that substituent large enough that we can actually quote unquote lock a chair position, and we would no longer see the ring flip that we've talked about, because this group becomes so big that if we put it in the axial position, there is so much strain that it's no longer equal. So we can actually lock lock a chair conformation so that we no longer see that ring flip if that group becomes big enough for us. Next, we're going to look at our di-substituted cyclohexanes. With our di-substituted cyclohexanes, we're going to go back to that cis or trans terminology. So remember, cis referred to the hydrogens being on the same side in a double bond. Trans referred to those hydrogens being on opposite sides in a double bond. So we're going to see the same thing here with our cyclohexanes. If we draw out our cyclohexane ring just in a nice planar notation, what this means for us is for a di-substituted ring is that both of our substituents would be on the same side. So this would be a cis conformation. So right now I have them drawn so that they are both pointing out at you. So if you look at my ring, the 2 methyl groups on it, they're both pointing out at you. They're at the screen. So this would be a cis connotation. We could make them so they're both pointing back. There's no change with that as well. The key is that they are on the same face of the ring. They're both on the same side of the ring. We can also look at this in the context of a trans ring. For a trans ring, we see that they are on the opposite sides. So for this, one of them would be pointing out at you if I've got my flat ring. So one of them is pointing out at you. One of them is back behind the plane. Again, it doesn't matter which is which. All that matters is that we see different faces. We've got one on a top face. We have one on a bottom face. One of the other ways that we can denote this cis-trans in our dye-substituted rings is we can do what we call a Haworth projection. These are really used to tell you about those faces, to say whether things are cis or whether things are trans. It's really the only thing that they are good for. And in this type of projection, what we're going to do is we are going to make the ring parallel to the floor. So I've tried to darken in what would be coming out at you. What is in the normal bonds is what's going back behind. So you can kind of think about this as I have put this ring in flat notation and flat with the floor. So then when I actually look at this, I can have what we call the top face and what we call the bottom face. So you can see this would be cis. All the substituents are on the top face of my cyclohexane ring. If we do the trans notation for this, I could put one going up on the top and then one going down on the bottom. So this would have on our Haworth projection one coming up and one going down beneath. So these really don't represent too much other than that. They give us that cis-trans notation of what is on the top face of our ring, what is on the bottom face of the ring. We really don't use them very often in terms of reactivity. You will see this type of projection a lot with sugars. So if you're going to take biochemistry or you do any work with that, you will see this type of notation a lot with sugars to denote those different faces and what groups are all on one side of a ring compared to the other is when you'll really see more of these projections. So the first one that I want to look at for our dye-substituted cyclohexane is going to be a cis-1,3 dimethyl cyclohexane. So if I draw this out like we have been drawing our structures just in a nice planar fashion, what this would mean for us is I would have a methyl group in position 1, I would have a methyl group in position number 2, and what you have noticed is I've darkened both of those in. I've made sure to say these are both on the same face. They are both pointing out at you if I have a nice flat ring that we're looking at. So what we want to talk about with this is we now need to compare our two chairs. In terms of are the chairs equal, are they not equal, and to do that we have to be able to decide what is in the axial position and what is going to be in the equatorial position. So I'm just going to start off by drawing one of my chairs, and then I'm going to put in my positions. So it does not matter once again where you start, so I'm just going to start here with my CH3 and I'm going to point it directly up. And I'm going to put the hydrogen in so we can see that that CH3 is in the axial position, and then I've got the hydrogen in the equatorial position. I'm then going to count around 3 carbons, which would put me here if I count towards the front. And now I need to put my CH3 on the same side of the molecule. So since it is on the top face in that axial position, I need to put it on the top face as well, which would put it in the axial position in that 1,3 position. So then when I get ready to do my chair flip or my ring flip, I'm going to go ahead and keep everything the same. So my carbon still has to have the methyl group pointing up. So now it is in the equatorial position. The hydrogen is pointing down and in the axial position. Counting around 3 carbon atoms, I still have my methyl group. And my hydrogen pointing down, where once again now that methyl group is still in the equatorial position and that hydrogen is once again in the axial position. So now I need to compare these in terms of stability. So here both of my CH3s are axial. Here both of my CH3s are equatorial. So based on what we just talked about in terms of stability, the one where I've got all my groups in the equatorial position is going to be much more stable than the position where they are in the axial position, where we have that strain. So if we look at it on my model kit, so there it is on my model kit where we've got the two CH3s and they're in that axial position. You'll notice up here at the top, those two groups are very, very close to each other. That's that 1,3 diaxial strain. Since they are both large groups, it's a very high strain. They're very close. I can almost make those hydrogen atoms touch. I can form a bond there with my kit. So it's a very strong interaction. When I get ready to flip them then into the other chair, now they're out here in these axial positions. And if I continue to rotate around, it's out here in this axial position where there is no interaction. We would have those anti-conformations if we look down the line. Everything is anti in relationship to that staggered conformation. So when they are both equatorial, they are more stable. I have shown that in this structure by using those equilibrium arrows that you're familiar with from your Gen Chem course, and I have favored now the equatorial chair position. So we can show which ring flip is favored through the use of those quote-unquote equilibrium arrows, where we have the longer arrow to the side that is more favored, and we have the shorter arrow to the side that is less favored. The next one we're going to look at is going to be the trans 1,3-dimethyl cyclohexane. So again, I'm going to draw in that cyclohexane, but this time the CH3 units are on opposite sides in that 1,3 position. So I'll have one of them on the top face and I will have one of them on the bottom face for that trans 1,3 dimethyl cyclohexane. So again, we're going to do that same comparison. We're going to see which one of the chairs is more favored based on these positions. So for my chair number 1, we're going to go ahead, and again, I can fill them in however I want to fill them in. So I'm going to go ahead and put one of my methyl groups in the equatorial position and pointing down on that top carbon. I'm then going to count around 3 positions, and I need to have this methyl group on the opposite face. So since that first CH3 is pointing down, my next CH3 needs to point up, and the up position on that carbon atom is the axial position that we're going to be looking at. So if we look at this in terms of my kit, we have one of them in the equatorial position. When I count around, I now have one of them in the axial position as well. And this is to denote that trans relationship, opposite faces that we're going to be dealing with. So you'll notice one is on the bottom face, so if I make this so it looks flat in the screen, one is pointing back, one is pointing out at you. So they are on opposite faces for us. When I then get ready to do my ring flip, so for my ring flip, that CH3 that was pointing down still needs to be on the bottom face. It still needs to be pointing down, but now it is going to be in that axial position. When I go to carbon atom number 3, that CH3 still needs to be pointing up, but again, now that up position is in the equatorial position. So if I go ahead and I flip my ring from the way it originally was, we will see those two positions flip. One becomes now axial, and the other one now becomes the equatorial position. So if we do our count here, in this one I have one axial CH3, and then I have one equatorial CH3. If I look at the one on the other side, I still have one axial CH3, and I have one equatorial CH3. So with this now, there is no difference. And if we compare them, one is not better than the other because of the different positions that we have. So these two chairs are equivalent, and we would see that interfluctuation between the two chairs. We will not favor one over the other because we have the same substituents in each of the positions, axial and equatorial. So for the next one we're going to look at two different groups in our disubstituted cyclohexane. So we're still going to be looking at our trans conformation, but this time we're going to have one ethyl and two methyl. So here I'm going to have my ethyl group, and I'm just going to make it point out. On the third carbon atom, I'm going to have my methyl group, and it's going to be pointing back. So again, the key here is that trans relationship where we have one pointing out and one pointing back. So again, just to start off and to draw my structures, to look at my 2 chair conformations, initially it is up to me to figure out where I want to draw them. So I'm just going to make my methyl group up here at the top. So here would be my methyl group. I'm going to place it in the equatorial position, so pointing down. I'm going to count around my 3 carbon atoms, and then I'm going to have my ethyl group, and it needs to be on the opposite face. So since the methyl was on the bottom face, the ethyl now needs to be on the top face or pointing up, which is the axial position on that 3rd carbon atom. And my hydrogen would be then in the equatorial pointing down. So remember, ME is my abbreviation for methyl. ET is my abbreviation for ethyl. We will see these used again periodically to kind of shorten up what we are looking at. So this is one of my positions where again I have one in the axial and one in the equatorial position. So now I'm going to do my ring flip. And with my ring flip, that methyl group is now going to be in the axial position because it still needs to be on that bottom face. The hydrogen will be up in the equatorial position. The ethyl group is still pointing up, but now that position is the equatorial position. And my hydrogen is then in the down position, which is the axial position. So again, we still see that my ME this time is the equatorial. My ET, my ethyl, is in the axial. If we look at the other one here, the ME, the methyl group, is in the axial, and my ET is in the equatorial position. So I still see one equatorial and one axial on either one, but now we need to decide does the size of the group matter in terms of where we're going to place it. So if we look at my kit, the kit that I have drawn here is the very first one we drew, where I've got my methyl in the equatorial position, lots of space around it, and I have the ethyl up here in my axial position. And you'll notice it's a very large group. So depending on how I rotate it, there are times that it has a heavy interaction, that 1,3-diaxial strain, with those other hydrogens that are there at the top. Again, to the point where we can almost connect them if I wanted to and make a bond with my kit. So then when I get ready to switch them, and I'm going to put my methyl group in that axial position. So here's the strain. There's still that 1,3-diaxial strain, but it's not nearly as close. I can't reach out and form a bond with that methyl group and with the hydrogen. And then I have my equatorial position, my ethyl group out here, and it's got lots of freedom of rotation, and it's got lots of area where it can continue to rotate and rotate. So when we look at these 2 groups, they're not created equal. And what we're going to see is that when we have the ethyl group in the equatorial position compared to the axial position, it is once again much more stable for us. So what we're going to see with these groups is even though I've got an axial and an equatorial on each one of my chair conformations, I'm going to favor the one that has the larger group in the equatorial position. And we're going to see that with all of our chairs. So what we want to be watching for here is you do want to be able to do different orientations of those di-substituted, or even if we look at tri-substituted or putting more substituents on our ring in terms of the trans and the cis relationship. So I would encourage you to practice some more with those trans and cis relationships in positions other than 1 and 3 and looking at the relationships that they have. Because remember, when they are on adjacent carbon atoms, the axial positions are on opposite faces, axial up, axial down. Compared to the 1-3 relationship that we were looking at, it was axial down in that 1-3 relationship. So the relationship that the substituents have to each other within the carbon chain is also going to play a role in the position that they have in terms of axial and equatorial. But our biggest goal that we're going to be looking at with all of these and determining which chair is the most stable is we want substituents to be in the equatorial positions. And if we have options, we would prefer that the larger substituent be in the more stable equatorial position.